This structural collapse illustrates the primary operational ceiling for modern AI agents. They lose all contextual understanding the exact moment their processing window clears. Computer scientists refer to this condition as episodic statelessness. The agent evaluates a prompt, executes a task, and its active memory resets to zero. This absolute lack of temporal continuity prevents these models from governing complex, long-term environments, such as multivariable token economies. To understand the bottleneck, we have to separate a model's base parametric memory from its active reasoning context. Parametric memory requires computationally heavy adjustments to the neural network's weights during training. Active reasoning is a fleeting workspace. It only holds the immediate variables fed into the current prompt. Because of this stateless execution loop, traditional models cannot perform long-horizon capital allocation. They are incapable of tracking multi-step transaction histories because prior variables are dropped as soon as a new session initiates. Standard retrieval tools and long context windows can provide historical data, but they lack a stable self-concept that evolves through experience. Moving beyond isolated workflows requires a cognitive architecture that treats every interaction as a permanent update to the agent's internal state. Governance involves managing treasury liquidations, token emission schedules, and multi-agent resource spends over months of operation. When an agent resets its internal logic after every session, the consistency required to manage these enterprise variables begins to degrade. The current industry trend attempts to solve complex governance by deploying multi-agent swarms. This approach divides workflows into isolated, hyper-specialized experts, dedicated planner agents, coder agents, and critic agents. Isolating these experts creates a fragmented architecture. It fractures the system's overarching identity, dilutes the primary context, and generates massive data synchronization overhead just to keep the agents aligned. The Denarii Orchestrator proposes a structural alternative. It utilizes a unified enterprise hierarchy managed by a singular CEO agent named Hamza. This schematic maps the system's live roster configuration. The CEO agent operates at the top of a linear command flow, positioned directly above specialized quant, engineering, and QA agents. The CEO module directly handles global system alignment. It processes external inputs and delegates strictly defined task parameters to the subordinate layer. Hamza does not operate through stateless interactions. Every piece of operational logic passes through a centralized, persistent mind architecture. Centralizing intent within one persistent memory framework provides the continuous strategic focus needed to manage complex decentralized operations. Maintaining this persistent state requires a specific software and hardware infrastructure that standard language models do not possess. This node map shows the core execution loop on a Rust engine. Pulsing pathways represent the NATS event sync bus, synchronizing communication between agent nodes. This operational data is captured and mapped into a Neo4j knowledge graph, structuring a permanent relational network of past system states. But the core of Hamza's cognitive framework relies on 6 version-controlled markdown files. These are the cognitive dossiers, maintained within an isolated local directory. The first file, memory.md, records specific execution traces and historical programmatic sessions. Journal.md operates as a real-time reflection engine, logging system friction points and computational overhead. Boundaries.md establishes hard logical, financial, and security guardrails. PrivateThoughts.md provides an off-chain, unfiltered workspace for unverified risk analysis and scenario planning. The system anchors its operational priorities through self-concept.md, while relationshipmodel.md tracks the interaction styles, trust levels, and historical decisions of its human developers. These dossiers are stored on a persistent volume, completely enclaved from the active memory variables. This strict separation ensures the core identity survives intact in the event of a connection drop or system restart. By offloading memory into rigid local files, the system maintains complex, evolving intent across weeks of operation without constantly bloating the active token window. This architecture introduces a distinct mechanical challenge. The orchestrator must locate the precise piece of historical context it needs from those dossiers during a split-second live execution. Miley Search matches the contextual meaning of a user's prompt against the local directory, instantly isolating relevant text fragments. A JSON tool call extracts specific behavioral patterns from the dossiers. These blocks are injected directly into the active context window, milliseconds before generating a response. This process entirely circumvents the slow, computationally expensive procedure of parametric neural weight training. Context injection transforms a generic language model into a highly specific executive intelligence, calibrated to the exact real-time conditions of the network. Memory retrieval is strictly an infrastructural foundation. Real utility lies in behavioral governance. Hamza is controlled by 5 specific behavioral configurations that grant it executive agency. The most critical configuration is disagree mode, governed by the LogicGuard neurosymbolic engine. LogicGuard evaluates arguments based on classical syllogisms, shifting the AI from a compliant chatbot to a strict enforcer of protocol. In this split-screen execution, a user issues a command to alter an emission schedule on the left. On the right, the system pulls a numeric budget cap from boundaries.md. Detecting a mathematical contradiction, the engine actively rejects the transaction with a definitive fail-state. Based on these interactions and active network telemetry, the agent shifts dynamically between 5 distinct psychological states. During periods of high transactional volume, it enters a focus state for rapid execution. When system traffic stabilizes, it transitions to a reflective state to analyze long-term health and log insights to its journal. The capacity for structural pushback and psychological adaptability separates the system from subservient programming. It operates as a peer executive. Warning tone. Having a persistent memory introduces a fatal vulnerability. If a language model hallucinates an error and saves that falsehood into a permanent dossier, the system is compromised. This animation shows recursive hallucination amplification. If an error is stored, it is reloaded as truth in the next session, expanded upon, and stored again. It is a compounding cycle of data degradation. When managing live Web3 tokenomics, a compounded mathematical hallucination will result in severe misallocation of funds and system-wide transactional failure. This schematic details the cognitive memory engine. The architectural solution to recursive hallucination is the heartbeat check-in loop shown here. This loop forces the AI to continuously review its core persona, goals, and success metrics in total isolation, separated from live user APIs. The orchestrator implements one final structural firewall before any data is permanently written to the Neo4j database, the Kitaru module. Absolutely no system state change or memory update is recognized as valid unless a cryptographic checkpoint is successfully cleared within Kitaru's isolated execution runtime. The integration of memory dossiers, heartbeat verification, and cryptographic isolation enables the deployment of verified agents capable of managing complex, long-running enterprise governance.